In part 1, we found that our system is capable of holding 6 psi regardless of how many valves we have opened, that we have plenty of extra motor speed to help PID accelerate quickly, and which motor speeds correspond to the min and max sensor readings. Now we just enter the PID-related parameters and turn it on, right? Well, in theory, yes, but there are a lot of parameters to keep track of, which can make PID seem overwhelming. The good news is, I've sifted through all the related parameters and pulled out the bare minimum you'll need to get up and running quickly and arranged them into an Excel spreadsheet configuration tool that looks like this. It's just your basic feedback diagram where we take the set point and the process variable, take the difference, produce an error signal, run that through the PID algorithm, and send the control output to the motor. The parameters associated with each of those are grouped around each item, plus the motor control group, the drive control group, and the display configuration parameters. This legend tells you what all the colors mean. All of the blue parameters are factory defaults, and the gray cells are read-only. So all we have to do is take one group at a time and fill in the yellow blanks. When we do, those turn white. Before we get started, please note that this worksheet applies only to the WEG CFW500 drive's built-in PID. It doesn't apply to the internal or external PLC application versions of PID that the CFW500 also has. We'll do a separate version of this for those. And this is a summary of how the system is set up. I'm using this drive exactly as we left it in part 1, where we had done a factory reset so you know exactly where I'm starting from. We entered the motor parameters you see here in white and the display parameters shown in white. Let's enter the min and max drive frequency parameters we found in the previous video just to finish that section. Great, all the yellow cells are gone and that section's done. Now when you press the up-down arrow keys on the keypad, the result gets converted to engineering units and stored here. It's gray to remind us it's read-only. This is the value we want to show on the display. The raw set point in percent is stored in parameter 525. We want 6 psi, which is 40% of our sensor's 15 psi range, so we put a 40 here. The filter is for when you have an analog input for your set point. We're entering the set point from the HMI keypad, so filtering doesn't matter. We'll leave that at the blue default value. If you see a little red triangle in the cell, then there's a hover note explaining what I did or listing relevant options. For most applications, you'll find that these blue default PID coefficients will be a great starting point, especially for monitoring pressure and pumping applications. The manual has this awesome chart that gives you good values to start with for other types of applications, like flow, temperature, etc. So I highly recommend starting with the values in this table. If you want to tweak those, well, check out this video. It shows you how to tune a loop on a CFW300 drive. The techniques shown in that video apply exactly the same way to the CFW500 drive. Let's set up the drive control. To keep things simple, we're going to set this drive up for remote mode only. That way we don't have to remember to make sure what mode we're in. Again, the little red triangle reminds us there's a note that has all the relevant options listed out. Looks like we want a 1 for remote only, so I'll enter that here. We'll use the HMI for speed reference, or set point. The drive defaults to having a digital input control run stop in remote mode, so we'll keep that blue default value too. Digital input 1 is the default for run stop in remote mode, so that's good too. And we'll use digital input 2 to control the manual auto operation of the PID loop, which is a 22. Now that means digital input 2 controls this guy. When we flip that switch to auto, the PID loop runs normally. When we flip him to manual, it stops the PID process and allows us to manually enter whatever value we want to appear at the control output. We enter that value in parameter 121 in Hertz. We'll set that to 0 just so we don't get any surprises when we turn this thing on. Bumpless mode prevents large changes or bumps in the control output when you switch from manual to automatic mode. Suppose you're messing with the system in manual mode, and then you switch to automatic mode. Well, because you were messing with the control output, the process variable could now be nowhere near the set point. That creates a large difference, which can create a large sudden change in the output, which could be hard on your system or possibly even dangerous. If you enable bumpless mode and you're using the HMI for the set point, the drive simply copies the current process variable into the set point, which guarantees there won't be a large difference. Once PID is up and running, you can then readjust the set point back to where you want it. We'll leave that off for this demo just to keep things simple, but most of the time, yeah, you'll probably want that enabled. Check out the bumpless video to learn more about that feature. Each drive does it a little differently, but the video will give you a better understanding of the kinds of things to expect. The process variable is stored in engineering units in parameter 40. Again, it's grayed out to remind us it's read-only. We have a forward acting system, so we'll leave that at the default. Forward, or direct acting, means the pressure goes up when the motor speed goes up. A reverse acting system would be like a cooling system, where the temperature goes down when the motor speed goes up. We're using analog input 1 for our process variable. This also enables PID. To disable PID, set this to a 0. This guy creates a dead zone for small analog signals. We don't want that messing with our PID calculations, so leave it inactive. We don't need to change the gain. We're using the default 0 to 10 analog input, and we don't need an offset, so we'll leave all of those at the default blue values. I like to add a little filtering on my analog inputs to help reduce noise, but you'll want to keep this as small as possible because it will slow down the PID response. Learn more about noise reduction in this video. Finally, we need to configure the display. We want to end up with the set point in PSI on the first line of the display because that's the line that the keypad's up-down arrow keys control. The process variable on the second line also in PSI, and the motor's current on the bar graph. The motor's RPM is always in the upper right, so we get that for free. I marked all of the display locations in red on our spreadsheet. Parameter 205 is what we want to show on the first line, so we put the set point in engineering units there. If we wanted to show a percent value, then we would put this guy there. We want a 15 psi scale with 1 decimal point, so that's a 150. We want the process variable in psi on the second line of display, so we put that here. And it uses the same scaling. Output current is the default for the bar graph, and this drive can output 4.3 amps, so we'll leave those at the default too. Well look, all the yellow cells are gone, which means we're done configuring parameters. I went ahead and entered all those into the drive to save us some time. Here's our test station. I'm going to zoom in on the display and the switches so you can see what I'm doing. Let's start with PID in manual mode. Remember, that's where we bypass PID and we manually force the control output to the motor to whatever we want it to be. I'll switch to run, and because the set point is currently 0, the drive spins the motor up to the min output frequency we specified in parameter 133, which comes out as this many RPMs. That min frequency we found in a previous video should give us close to 0 psi, and it does. If we manually increase the motor speed, nothing happens until we get to the minimum speed we put in parameter 133, and then the RPMs and the system pressure start going up. Perfect. I'll adjust the motor speed to get the system pressure to 6 psi. And sure enough, this is the same RPM we found we needed in a previous video to maintain 6 psi with one valve open. I'll open another valve. The system pressure drops. I'll increase the RPMs to get back to 6 psi. Open another valve. System pressure drops. Increase the motor speed to get back to 6 psi. Open a third valve. Same thing. This is exactly what we did in the previous video, isn't it? We manually adjusted the motor speed to compensate for the valves opening and closing. And that's what manual mode does. It allows us to manually control the system after PID is all set up. Let's go back to one valve, but I'm not going to adjust the speed to get us back to 6 psi. We see the pressure went way up. Instead, let's simply switch to automatic mode and let PID do it for us. And yep, PID automatically adjusted the motor speed to get back to the 6 psi set point. Open a second valve, and PID automatically adjusts the motor speed to compensate almost as fast as I can switch the valve. 3 valves, same thing. PID automatically compensates. 4 valves, same thing. What if I want to run the system at 5 psi? No problem. Just change the set point, and as quick as I can change it, PID automatically adjusts the motor speed to compensate, regardless of how many valves I have open. How about 7 psi? Same thing. PID automatically adjusts the motor speed so that no matter how many valves I open or close, the system automatically maintains 7 psi. So that's it. You should now have a pretty good idea of how to get PID up and running on a WEG CFW 500 variable frequency drive. You'll find a link to this configuration tool, wiring diagrams, etc. in the YouTube description below the video. Meanwhile, click here to learn more about the WEG CFW 500 family of variable frequency drives. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish new videos like this one.